So my name is Pedro, I'm from Portugal, and I'm doing my PhD under Staffan Lindenberg and Tommy Jonsson's supervision, and I'm working with them on various projects, but my main project, PhD project, is about zonulin. So it's about intestinal permeability, inflammation, and how that relates to insulin sensitivity, insulin resistance. And today what I'm going to talk about is what happened since the Paleolithic era until today that perhaps is the main explanation for the big rise in so-called Western or chronic degenerative diseases. But before I do that, I have to say that I'm very nervous because I'm about to speak after all of my, or most of my mentors have spoken before. So this is a big responsibility for me. I'm the new kid on the block, and these people are people that I look from from below, and they have helped me, they have taught me a lot. There's another person that I have also to say that also taught me a lot, which is Professor Laurent Cordain. So all of them, they've really helped me, and the very little knowledge that I have, I owe in a big part to them. So without that, without them, I wouldn't be able to be here today, speaking with you, and which for you perhaps could be a good thing. So let's start. So we know that about 160,000 years ago, like Professor Fritz Mosquit has said, we have the emergence of Homo sapiens in Southeast Africa. And we know that during the period that led to the appearance of Homo sapiens, and then for most of the time that Homo sapiens were on Earth, these people were hunter-gatherers. And so they led the lifestyle and the diet of a hunter-gatherer. And about 50 to 60,000 years ago, they decided to take a plane tour and leave Africa and occupy the entire planet. So whenever you talk about a Paleolithic diet, there wasn't one single Paleolithic diet, there wasn't one single Paleolithic lifestyle. It depended. If you were on the African savanna, the diet and lifestyle was different than if you were, for instance, on a tropical beach, or than if you were, for instance, on the Amazon jungle. But there were common universal characteristics on all of these diets, on all of these lifestyles during the Paleolithic era. Paleolithic means the old Stone Age. And Neolithic means the new Stone Age. And during the Paleolithic era, we were hunter-gatherers. But the lifestyle and diet was not the same. For instance, we know that although we occupied various parts of the planet, we maintain until about 40 to 35,000 years ago, most Homo sapiens occupied lower latitudes. And so if they occupied lower latitudes, they were exposed to ultraviolet B radiation in a frequency that allowed for the synthesis of vitamin D. Also, we know that when you look, and this is data from Professor Fritz Mosquit's lab, when you look at people that today live in the same area where supposedly Homo sapiens appeared, which is in this case Tanzania, and you look at the Maasai, which are pastoralists, and the Hadza, which are hunter-gatherers, so people who are outdoor, who live outdoor, you see that their average 25-hydroxy vitamin D3 is 42 nanograms per milliliter, which is 105 nanomoles per liter. So this is the average 25-hydroxy vitamin D. So whenever we talk about what is the number in terms of the 25-hydroxy D that we are supposed to aim for in human beings, I say that we should go back in order to find what is the optimal range. So instead of just looking at people who are not exposed to the sun, who are not living in the natural environment where all of us used to live, I think that's not the best place to look for. I think the best place to look for is for people who still live that life. But also we know that the sun is much more than vitamin D. We produce various photoproducts. Also from vitamin D we produce supersterols. So all of these molecules I guess they will have a function. And now there is evidence that they will do. So our body is not stupid, our body is not the government. Our body, when he decides to produce something, it's because it's useful, okay? Also, we know that ultraviolet A radiation was also another type of ultraviolet radiation that we were exposed to in lower latitudes, and we know that ultraviolet A radiation lowers blood pressure. So the sun is much more than just vitamin D. And this is one universal characteristic until we decided to occupy northern or southern latitudes, very far from the equator. Until then, we were able to be exposed to ultraviolet B and ultraviolet A radiation in a way that would give us, supposedly, various benefits besides the vitamin D. Also, we know that in all of these people, physical activity was mandatory because it was vital for survival. We also know that all of these people slept in sync with the daily variation in light exposure. We also know that these people ate a diet that could have more fish, less fish, more meat, less meat, more tubers, less tubers, more fruit, less fruit. But this diet was a diet composed of minimally processed wild plants and wild animals. And more important than what they ate, because it varied according to the ecosystem exploited, and according to latitude, and according to climate, more important than that is what they didn't eat. So what couldn't have been eaten by them. So sugar in the way that we eat today or drink today, alcohol in a way that we drink today. Of course, with the fermented fruit, they could get a high, I would assume, but it's not the same as it happens today. Also, the fats that they would eat were the fats that were naturally present in foods, not isolated from foods like we do it today. Also, the meat was meat from wild animals and not processed meat as we do it today. And the cereal grains, they were only started to be consumed in the late Paleolithic by some populations, but as a starvation food, so as a food that they had to start eating because the other foods that they prefer were not available. And of course, it was not in this form that they would eat grains. And the other one is milk from another mammal and dairy products in general. We know that milk from another mammal couldn't have been eaten or drank in this case. Why? And to know this, you really need to be a rocket scientist. Have you ever approached a wild animal? Now try to milk it. Okay? But we know that breastfeeding lasted longer than it lasts today. So it lasted on average about 30 months. Now to get a woman to be able to breastfeed her infant for 6 months is a big challenge for her, unfortunately because of social, economic pressures. So this is something also to consider, the breastfeeding patterns. And we know that until they continue their trip, and about 25,000 years ago, you see that they start to occupy northern latitudes. And when they start to occupy northern latitudes, as Professor Susan New has already mentioned, they could have vitamin D deficiency. We know that when you are at the equator, you can synthesize vitamin D all year. But as you move farther away from the equator and you pass the 35 degrees latitude limit, you start to have vitamin D deficiency during 1 or more months per year. And if you go to where my supervisors are and where I go there, but I don't go there for a long period of time, and now you understand why. So they can get vitamin D deficiency for 6 months or more. This was a change, but about 10,000 to 15,000 years ago, the Neolithic or agricultural revolution began. And this was the biggest change in our history. And this brought the domestication of animals, as Professor Fritz Mosquito has already mentioned, and it brought the domestication of wheat and barley in the Middle East and rice in what is today China. And a little later you have the domestication of corn in southern Mexico, and the first evidence of dairying comes from Turkey from about 8.5 thousand years ago. And if you look at the human generations, we are talking about 330 human generations. But if you look at the number of generations since the appearance of Homo sapiens, we are talking about of more than 6,000 human generations. So if you look at this and our time as Homo sapiens, this represents only 5% of our time on Earth as Homo sapiens, and it represents much less than that of our time on Earth as hominins. So this is something that we should also consider. And about 200 years ago, the Industrial Revolution began, and the Industrial Revolution brought, for instance, refined sugar. This is the United Kingdom, data from the beginning of the 19th century to more or less the decade where I was born. And you see a big rise in refined sugar consumption. So the Industrial Revolution brought sugar for everyone. It brought also feedlot meat from obese animals instead of wild animals. So the fatty acid profile is different, of course. Refined grains for everyone. Refined vegetable oils for everyone. Hydrogenated fats at the beginning of the 20th century. And then in our era, I see what I call the disaster, which is all of this. So the junk food. So all of this, unfortunately, synergizes with physical inactivity. So if you think about this and physical inactivity, you already have one of the explanations, but it's not the only one. And if you look at physical inactivity in man, for instance, you see that most of the Western world is physically inactive. If you look here at the United Kingdom, you see that about 50% or more of men and about 50% or more of women, they are physically inactive. So they are sedentary. So this is how we are evolving today. And this, of course, is a cause of concern. Also, we now have much more chronic psychological stress instead of acute stress like we did in the past. Also, the sleep habits today are very different. If you look at the old ways, you would see that in the evening you wouldn't have light. So you would either have sex or go to sleep. Today, you have light during the night. So this means that you are having sex with the light, or it means that you are working or doing something else. You're not sleeping. So this is important because we know that sleep restriction in humans under control conditions decreases insulin sensitivity, increases inflammation, decreases endothelial dependent vasodilation, and also we know that working in shifts seems to be associated with an increased risk of cardiovascular disease and various types of cancer. Also today we have a lack of sun exposure, because we protect from the sun or we simply avoid the sun. Also, today, we are exposed to a toxic environment. So if you look at what happens today, you have various pollutants in our food chain, in the air that we breathe, the water that we drink. And it's something that it's not going away, unfortunately. Also, if you look at, for instance, children, but also adults, in a more traditional context, you see that they are exposed to various microorganisms. But today, children are told that they have to wash their hands and also that they have to take an antibiotic, even if they are infected with a virus. And so this is also a problem, because this explains why, for instance, the Yanomami, which are a hunter-gatherer population from the Amazon jungle, have a much more diverse microbiota than, for instance, the Americans do. This is in fecal samples and this is in skin samples. So you see that there is more diversity in their microbiota. What are the big implications of this? Nobody really knows, but we suspect that this increases the risk for various chronic inflammatory, autoimmune and allergic diseases. So the big changes were increased xenobiotic exposure, so exposure to pollutants, chronic psychological stress, disruption of the normal circadian rhythm, altered UV exposure, physical inactivity, excessive hygiene, and an altered microbiota, and of course the Western diet. And many of you here are here because you want to hear about the diet. You want to hear about nutrition. So let's talk about the Western diet, the consequences of the Western diet. So let's talk about those. There were various consequences. One of them was an altered fatty acid balance. So Professor Michael Crawford already mentioned the altered fatty acid balance. But I just want to add something to it. We know that today we are eating a lot of linoleic acid. It's an omega-6 fatty acid, 18 carbons, 2 unsaturations. So linoleic acid, we know that it will replace EPA and DHA in the cell membrane. So you will end up with less EPA and DHA in the cell membrane. So if you look, for instance, here at pregnant women in Canada, you see that linoleic acid is associated with a decrease in EPA in red blood cell membranes and with a decrease in DHA in red blood cell membranes. So this altered fatty acid profile that happens today because of the diet that we are following can have various implications in terms of chronic disease risk. Besides this, we have a decreased micronutrient density. Everyone knows that processed foods, they lack various vitamins and minerals, but some of you perhaps do not completely realize that on a calorie basis, cereal grains, they cannot outrun meat, fish, fruits, and vegetables. They have less vitamin B content, they don't have vitamin C, they don't have vitamin B12. Also, they have a lower mineral content, and even if they contain adequate amounts of various minerals, we know that for iron, zinc, calcium, and magnesium, the absorption rate from cereal grains, whole cereal grains, of course, if they are refined, they won't have almost any nutrients, but if they are whole grains, we also have phytate, which will decrease all the divalent ions absorption. So calcium, magnesium, zinc, and iron. So this is something also to consider. Perhaps if we decrease grains and we increase the intake of fruits and vegetables, fish, meat, we would increase our micronutrient intake also. And then we also have, and Professor Linda Frassetto has already mentioned, that we have an increase in the sodium to potassium ratio. We have also an altered balance between sodium and calcium, sodium and magnesium. And also we have an increase in the chloride bicarbonate ratio in our diet. So today we have processed foods, luncheon meats, salted cheeses and added salt, and we have a decrease in the intake of fruits, vegetables, and tubers. So this will explain this altered ion balance that I just mentioned. And this, of course, comes with an increased net acid load that Professor Linda Frassetto already mentioned. Besides this, we also have an increased intake of the so-called acellular carbohydrates and a decrease in fiber intake and in prebiotic intake. So these types of food contain acellular carbohydrates, contain very little fiber, very little prebiotics. So this would alter, along with antibiotics, will alter our microbiota, and this could lead to chronic inflammation and to diseases that are related to inflammation. We know that inflammation appears to increase the risk for insulin resistance. It appears to lead to dyslipidemia and atherosclerosis, is involved in various types of cancer, is also a cause of sarcopenia and osteopenia. For those who do research or who know more about bone metabolism, just look at the RUNC-L and the RUNC to understand that inflammation is, of course, one of the causes of osteoporosis that starts with osteopenia. Also, neurologic and psychiatric disorders appear to be related, at least some of them, to chronic inflammation, and nutritional deficiencies like iron deficiency anemia is also a consequence of chronic inflammation. Just look at rheumatoid arthritis, where iron deficiency anemia sometimes is the biomarker that leads to the diagnosis, or that leads rheumatologists to try to figure out what happens with this person and find out that she has or he has rheumatoid arthritis. So now the question that comes up to me is, who is the master regulator in our cells and our immune cells of inflammation? And we have a master regulator called NF-kappa B. So nuclear factor kappa B. And this is a transcription factor. And this transcription factor, this is a leukocyte like a monocyte or a neutrophil. And this NF-kappa B that has two subunits, P50 and P65, it's not important to know it, is binded to this inhibitor of NF-kappa B. And when the three of them are bound, this NF-kappa B cannot leave the cytosol of the cell and migrate until the nucleus of the cell. But when we have inflammatory stimulus, we will activate a kinase that will lead to the phosphorylation of this inhibitor of NF-kappa B. And when this inhibitor of NF-kappa B is phosphorylated, it will be submitted to degradation by the ubiquitin proteasome system. And when it is degraded, then the NF-kappa B can finally leave the cytosol and go into the cell nucleus and bind the promoter region of various genes that code for inflammatory proteins like cytokines and like enzymes that participate in inflammation. So this will lead to inflammation. And at the same time, some of these cytokines will activate the same cascade in another leukocyte, which will amplify the inflammatory reaction. So now the question is, who activates or what activates this NF-kappa B pathway? Let's look at some. Let's look at pollutants, it's one of them. We know that adipokines, it's another one, and we know that when we eat this type of diet, a hypercaloric diet, and we are physically inactive, we will expand our adipose tissue, but then we will have a hypoxia and we will have the infiltration of macrophages. And then we will have the production of various cytokines, and all of these cytokines will increase inflammation through the NF-kappa B pathway. So we know that obesity, especially visceral obesity, is also a cause of inflammation. Also we have hyperglycemia as a cause of inflammation. So diabetes, of course, is a big problem, but also we should consider that these types of food will elicit a postprandial hyperglycemia. And if you eat it on a chronic basis, during various times of the day of your day, eating 6 or 7 times a day, like nutritionists like to say that we need to do, then you can end up with hyperglycemia and with an inflammatory response. Also, the increase in a cellular carbohydrates that I mentioned and the decrease in fiber and prebiotic intake also is associated with this that I just mentioned. Also, what we are doing with the foods, the way that we cook it, the way that we process it, we produce advanced glycation end products and advanced lipooxidation end products. And these types of foods, I mean, you don't need a scientist to tell you that this is not healthy. Every 3-year-old knows that this is not healthy, okay? But these foods contain a high amount of advanced glycation end products and advanced lipooxidation end products. This will activate the NF-kappa B pathway. So this is another thing to consider. Also, we have reactive oxygen species, also activating the NF-kappa B pathway. So what could lead to an increase in oxidative stress? Well, various factors can do it. Tobacco is one of them, so smoking, exposure to pollutants, being a pilot on an airplane, which I suppose none of you here is. But there are other factors, and one of them is related to our diet. So if you increase your intake of linoleic acid from sunflower oil, and you compare it to olive oil, you see that linoleic acid increases when you eat foods with this oil, sunflower oil. You see that linoleic acid increases in your lipoproteins, in your LDL lipoproteins, and you see that it increases. But you see another thing. You see that when you have more linoleic acid in your LDL, you also have more oxidized LDL. So this is something also to consider, that these vegetable oils, perhaps they are also contributing to oxidative stress. Think about it. Also we have trans fatty acids and also saturated fatty acids. Nevertheless, we should also look at things, as Professor Fritz Mosquito always says, in balance. So things should not be seen in isolation. And if you look at all these foods are rich in saturated fatty acids, many of them, but they are also rich in refined wheat flour and in sugar. So you have to look at things in combination and not only in isolation. Also, and this is something that I want to invest a little time on, which are pathogen-associated molecular patterns. Let's look at those. So here we have gram-positive bacteria, and here we have gram-negative bacteria. And in gram-negative bacteria, we have here lipopolysaccharides. These are barcodes. When you go to the supermarket and you want to buy food, you want to bring it to the counter, and the counter will read it with a scan, and the price will appear. It's the same in our immune cells. When a bacteria invades us, these lipopolysaccharides, these barcodes that exist in bacteria, they will be sensed, they will be scanned by receptors in our immune cells. These receptors are called toll-like receptors. And when they sense these lipopolysaccharides, these barcodes in bacteria, they know that they have to do something about it. So they will be activated. So here you see that LPS, when it binds toll-like receptors, it will activate the cascade that we just mentioned, the NF-κB, which will activate another leukocyte, and the process will go on and on. So we'll have an amplification of inflammation. So today, this endotoxemia, which means an increased concentration of lipopolysaccharides in our blood, is being seen as one cause of chronic degenerative diseases. Why? Because it increases inflammation. Inflammation will lead to various things like I just mentioned. So the next question is, where does LPS come from? I think the answer is obvious. It comes from our gut. But how can it access systemic circulation from our gut? We have walls in our gut. We have epithelial cells that won't allow it to happen. But let's look at this in a more detail. So here we have the villi, we have the enterocytes. Let's look at the enterocytes in more detail. And between the enterocytes we have the so-called tight junctions. And here we have, as Professor Michael Crawford mentioned before, the microvilli, where the lactase enzyme is. So let's look at this in more detail. So here is the normal enterocytes, let's say it like this, with the microvilli and with the tight junctions. So here we have integrity. But if you have an increased intestinal permeability because of compromised tight junctions, or because of an opening, a reversible opening of tight junctions that could be signaled by various things like bacteria and apparently also by some proteins in our diet, then you can have increased intestinal permeability. And then LPS can access systemic circulation. And if LPS accesses systemic circulation, this is through a pathway called the paracellular pathway, then you can end up with inflammation. So this is something that I am concerned about. And I don't think it's a coincidence that all of these diseases, these are autoimmune diseases, so chronic inflammatory diseases, and also type 2 diabetes, and also insulin resistance, which is not a disease but it can lead to disease, all of these have been associated with the increased intestinal hyperpermeability. So this is something that I would be concerned about. So the next question is, what causes intestinal hyperpermeability? Let's look at some of the causes. One of the causes is anti-inflammatory drugs. This has been known for many years now. The other cause is capsaicin that exists in peppers, for instance. But it's dose dependent, of course. If you eat a little bit, it's no problem. But if you eat a lot of it, it's something that, for me, it would be a concern because of this. Also, deficiency of zinc, deficiency of vitamin D can compromise the epithelial layer, the epithelial integrity. Also, we know that saponins that exist in legumes, in grains, but you can reduce its content by soaking grains, soaking legumes. They also increase intestinal permeability. Alcohol does it. It's very well known. So alcohol, it's not controversial. It's something well known. And also, we know that lectins that exist in certain foods like cereal grains could also increase intestinal permeability, and then we have gliadin that could increase intestinal permeability. Let's look at lectins and gliadin in more detail. For that, let's look at bread. Let's look at wheat. And we have, in wheat, we have glutenin, which is one protein that along with gliadin forms gluten. Then we have wheat germ-agglutinin, which is a lectin, and then we have these globulins, which are also inhibitors of these two enzymes, alpha amylase and trypsin. We'll go back to that later on. But let's look now at gliadin and wheat germ agglutinin. These two, and you have some of the references here, they appear to increase intestinal permeability in everyone, not just celiac disease people. But we need better data in order to prove this. So this is also a consequence of the Western diet, which is the introduction of novel proteins and bioactive compounds. And I'm not talking about phytochemicals in fruits and vegetables. I'm talking about bioactive compounds like gluten, for instance, like gliadin, like lectins. And we know that lectins and the wheat globulins, the alpha amylase trypsin inhibitors, they also activate the NF-κB. So looking at wheat germ agglutinin and the alpha in more detail, you see that when you do an in vitro study with wheat germ agglutinin in macrophages, you see that you increase TNF-alpha, interleukin beta, interleukin 12, and interferon gamma. All of these increase when you put that when you treat macrophages with wheat germ agglutinin. Also, let's look now at these globulins that exist in wheat, the alpha amylase trypsin inhibitors. They appear to bind the same toll-like receptor that LPS does, and this could lead to a release of pro-inflammatory cytokines, and this occurs in the cells of celiac and also non-celiac patients. What do we need now? We need intervention studies with wheat to know, whole wheat, to know if it increases inflammation or not. So that's something that we need, but so far I would say that it's at least prudent to reduce our wheat intake until we have better data. That would be my main message. But let's look at this study with the Western diet in non-diabetic subjects. They've eaten these fantastic foods. So here you have egg muffins and also this food that you have here, the hash browns. And this meal is composed of 50 grams of fat and more than 80 grams of carbohydrates, which is about 900 kilocalories. And what happened is that you see a 150% increase during a 3-hour period in the NF-κB binding activity in the nucleus. So this is, proof. This happens in mononuclear cells, in monocytes. So you isolate monocytes, so the people eat this meal, you isolate monocytes before and after, and you see these alterations in various proteins, in this case in this transcription factor. So you do transcriptome analysis, which is hard to do and it's very expensive. But it proves that this meal is pro-inflammatory. But you don't need this. Sorry, but you don't need this to know that this meal is crap. Okay? You don't need a study like this to know it. Besides that, we had also, with our new diet, suffered from an increased intake of isolated fructose and also an increase in the glycemic load of the diet and an increase in the insulinemic index of the foods that compose the diet. If you look at all of these foods, all of those have high sugar, high glycemic load, they will increase insulin. But not many people know that milk, although it has a very low glycemic index, a very low glycemic load, it will increase insulin more than glucose. And this has been shown in various studies. So one of the theories that my friend Bodo Melnik from Germany has come up with, and I tend to agree with it, and I will try to synthesize it, is this. So if you drink more milk, a lot of milk, you will increase insulin and we will also increase IGF-1. This could be good if you are thinking about growth. But this increase in the insulin in the IGF-1 will increase the signaling through their specific receptors, the insulin receptor and the IGF-1 receptor. This will activate AKT, which will activate the mTOR complex 1 pathway. I will come back to that mTOR pathway later on. But now let's just look at other ways that milk has to increase this pathway. Milk also contains proteins, of course it contains proteins, and those proteins are whey proteins that represent about 20% of the proteins in milk, and it contains the whey protein's leucine, which is a branched chain amino acid, and leucine will also will activate this pathway. And also we know that milk, 80% of its proteins are caseins, and caseins contain glutamine, and glutamine appears to increase the uptake of leucine by the cells. So this will increase the mTOR signal activation. Also we know that milk contains estrogens, and these estrogens also increase the uptake of leucine by the cells. Also we know that milk, in this case of course we are talking about whole milk or dairy products, they have palmitic acid, and palmitic acid also activates the mTOR complex 1. Also, and this is fairly new, milk contains microRNAs, and microRNAs, they will keep the mTOR complex 1 activated. So all of this, my friends, is normal if you think that activating this pathway will lead to increased growth. So this is good for survival, but this could not be good, perhaps it's not good if you are thinking about middle-aged people, sedentary middle-aged people. But there is a way to decrease the activation of the mTOR complex 1 pathway. You can increase AMP kinase. So this AMP-dependent kinase, how do you increase it? Well, I think you all know, of course, about ATP. So if you hydrolyze ATP, you'll get ADP. If you hydrolyze ADP, you'll get AMP, right? And AMP will activate this kinase. This is a sensor, a fuel sensor in our cells. So AMP-dependent kinase will be upregulated. And when AMP kinase is upregulated, then you will inactivate the mTOR complex 1 pathway. But if you eat a high glycemic load, a hypercaloric diet, you will increase glucose and ATP, and then you will not activate, of course, the AMP-dependent kinase. So then what will happen is that you won't have this break on your activation of the mTOR complex 1. So I'm not saying that milk is bad, per se, but milk in the context of the Western diet, I don't think it's the ideal option. Also, this meal will increase insulin, so you'll increase, of course, the signaling through the insulin receptor, so we'll increase more the activation of the mTOR pathway. And why the mTOR complex 1 overactivation is something that I'm concerned about? Because it is associated with increased protein synthesis. It will lead to increased protein synthesis, cell growth, and cell proliferation. So I'm concerned of someone who has cancer, for instance. Also, it could lead to fetal overgrowth. Also, it could lead to an increased adipogenesis. Also, it could lead to insulin resistance. It's always dose dependent, of course. So it's the dose that makes the poison, of course. And also it could lead to endoplasmic reticulum stress that is associated with what? Type 2 diabetes, beta cell failure. And it could also be associated with mechanisms involved in Alzheimer's disease. And it could also lead to early senescence, so premature aging. So this is something that I'm concerned about. People talk about caloric restriction, they talk about fasting as perhaps ways to increase longevity. Well, one of the ways that it could work, if it works, it could be because it decreases the mTOR complex 1 hyperactivation. So my friends, if we look at what we are doing today, you see that we have a suboptimal phenotype. We have the Western diet that leads to this. We have chronic stress. We have physical inactivity. We have inadequate sun exposure. We have inadequate circadian rhythms. We have excessive hygiene or overuse of antibiotics, an altered diet that with less prebiotics, less cellular carbohydrates, that could lead to an altered microbiota. And also, we have pollutants in our environment. All of this will lead to what I call a suboptimal phenotype. So as Professor Fritz Mosquito already mentioned, I think we should go back because we really messed up everything. He was a little more strong in his argument, but I'm still in my beginning, so I cannot speak like that. When I am his age, I will do it. I promise. But what happens if we really try to go back? And this is something that my supervisors have tried to do with intervention trials, with Paleolithic type diets. So this is a meta-analysis, a systematic review with meta-analysis with 4 randomized controlled trials. And it shows that the Paleolithic diet versus other prudent diets favors, it's better for a decrease in waist circumference, decrease in triglycerides, decrease in systolic blood pressure, and a decrease in diastolic blood pressure, and also a decrease in fasting blood glucose. Of course, we need much better studies, long-term studies, but that's, as Tommy has said, we don't have the money to do it. We don't have enough money, enough means to do it, but we want to do it. So at this point, I can say only this. You all have a choice in life, and your clients or patients, for those who are clinicians, will always have that choice. Everyone has a choice, of course. We have freedom of will. Until now we do. I don't know in the future. But so if we have freedom of will, we have a choice. And if we go in this direction, I don't think this will lead in a good direction. Also, if we go in this one, I don't think this is the ideal one. I don't know what will happen if we go in this direction, but I can tell you that it will be better than going in one of these directions. Well, now I will tell you this, and then I will die by a car. So in that case, that of course would be false. But if that doesn't happen, and I hope it doesn't, I think that going in this direction will be a much better choice. So this is something that I leave you to think about. Thank you very much, or as I say in my country, obrigado. Okay.
Thank you, Pedro, for a really terrific overview of pretty much the things that we've talked about today.
Thank you. Thank you.
That was great, you know. So if you had to say, you know, what are the most important things for us to do, you know, like the top 2 or 3, what would you say?
I would say eat in terms of the diet or everything?
In terms of, like, you know, here we are, we're saying this is good for you, but we have small studies and, you know, blah, blah, blah. So
I would say in terms of diet, I would say decrease, instead of being radical and say skip grains, and also grains unfortunately are necessary to feed the world's population because it's really big and increasing, as everyone already mentioned. I would say decrease grains and replace it with tubers, with fruits and vegetables as your main carbohydrate sources. You'll increase nutrient intake, vitamins and minerals, you'll increase fiber, prebiotic intake, and also you will decrease the intake of some bioactive compounds that could have potential adverse effects. The other thing I would say, reduce dairy, and instead of using dairy as your main protein source, use fish, eggs, protein as your protein source, meat as your protein source. Also, as your fat source, I would say fish, I would say avocados, I would say nuts, I would say the fat that is naturally present in the foods, the natural foods. Of course, if it's grass-fed, it's better than if it is fed with grains. And also, you have olive oil, which is very good to the economy of Portugal and Spain. And but olive oil, we know that since most of it is oleic acid, which is a monounsaturated fatty acid, it won't lead to the same effects that linoleic acid will do. But it also contains linoleic acid. So if you eat tons of olive oil, you will still get a decrease in your omega-3 index in your red blood cell membrane. So you should also compensate it by eating fish that contains the omega-3 fatty acids. And also, and this is something that people already know, decrease processed foods, decrease sugar, isolated sugar intake. I'm not very afraid of sugar that is naturally present in fruit, but I'm afraid of isolated sugar, especially in a liquid form. So this would be my main message in terms of the diet. And of course, try to exercise. You don't need to be an athlete, but you should be active. Try to sleep according to our natural environment, not according to the light. and try to avoid pollution as much as you can. If you can't, well, there's nothing you can do about it. And the other thing is try to control your stress. I would say that these things are not radical things, and this could lead to better health. But of course, I'm guessing, because we need more trials. But you won't have trials for everything. For instance, you don't have a study showing that when you jump from an airplane, that if you use a parachute, you won't die. For you to know that the parachute really decreases the risk of mortality by jumping from an airplane, you need to do a randomized controlled trial with a parachute and a placebo to see who dies. But since nobody has done it, we don't have evidence-based medicine will not allow you to say that parachutes reduce the risk of mortality. Some things are obvious, and I don't think we really need to do so many studies to show the obvious. But for other things, we really need trials to know. For instance, I need trials to know if wheat is really pro-inflammatory or not, if dairy really increases insulin resistance or not. For those kinds of things, I think we need more trials.